Who watches The Big Bang Theory? Good, yes. Almost 14 million years ago, everything started with a big bang. All this dust coming together 7 billion years ago produced a great deal of heat. And by about 4.5 billion years, that's the day they say, that's our birthday. It had cooled enough that there was a solid crust on the surface. And there's a good example. This is an example of somebody's countertop, the granite countertop. And there's just the various other examples here. And you'll see a big difference between this is an igneous rock, and these. Crystals are quite racist. They don't like to mix with others. As soon as rock starts to cool, all of the corundum minerals, for example, like to try and get together and make the biggest crystal that they can. And the slower it cools, the longer time they have to get together and make these big crystals. But if it cools fast, they don't get together, and the crystals are so tiny that you can't see them. Even the hardest rock, they begin to break down. The minerals that are formed under heat, like this, from a molten rock, they're not happy with the temperatures that you and I live in every day, and they get rained on, and they start to change. There's 3 ways that they change. One, they change into something soluble. You can see the rainwater has dissolved that, and it's dragging it down. So the magnetite in that rock, similar to this, has changed to a soluble mineral called limonite. The water is able to dissolve it and carry it down the side. The other way that it changes is there's a lot of feldspar in this rock, and feldspar, when you rain on it for 1 million years or so, will turn into clay. When that happens, the feldspar expands, and that starts to crack this rock, and it becomes very weak. See if you can snap that like a cracker. Yeah. And that and this are the same thing. It's just that this was dug out of a quarry, and this was probably sitting around on the surface for 1 million years or more. And 1 million years of rain and groundwater turns the feldspar into clay. And then when the feldspar is expanding, it cracks even the quartz. The quartz is the toughest mineral in here. But when it's surrounded by feldspar that's expanding, it cracks the quartz up into these tiny little grains. And the water carries those down. So we have some things dissolved, some things turn right into clay, and some things are broken down into little pieces. And all of that gets carried away by wind and water and deposited in the lowest area, a lake or a river bottom. And that gives us the second kind of rock. This was from a beach, actually, not far from here. You can see it up there when you're driving out to Canada, when you cross the big hill. This is a sandstone, so this is made up of the quartz that gets broken up here into tiny little pieces. When the feldspar swells, it breaks up the quartz into these tiny little grains, and you get sandstone. Does anybody know what we call clay when it's turned back into a rock? Shale. Same thing, it's just clay, but it's been hardened into a rock again. We call it shale. When a specialist looked at shale, they can tell you so much. As I say, it's almost like examining bodies. For example, they look at the brown and they say, okay, that the iron, the fine bits of iron in there have been rusted, like this hematite. And so it must have been exposed to the air. And then they look at the green and they say, well, that's similar to like ditch water. So it was probably a stagnant lagoon that the water level rose occasionally and exposed part of it, and then it came back up. And the other type of rock is from the minerals that are dissolved. And they're carried down the rivers and right out into the ocean usually because, they're easy to carry. They're just dissolved in the water. Calcium carbonate dissolves, not well, but well enough. And when it gets deposited again, it's called, nobody knows, this calcium carbonate, we call it?
Limestone?
Limestone, yep. And that's the most common rock you'll see around Ottawa. Most of the outcrops are this dull gray, and that's calcium carbonate, which originated from probably the calcium. They're probably both in the feldspar. Feldspar is a lot of different atoms in there. They probably came from the feldspar in the original igneous rock, and they're dissolved, washed down into the ocean, and deposited again. Sedimentary rocks, sometimes, if the basin that they're in, the lake or whatever, gets deeper and deeper and deeper, this pile gets very big. You get limestone, sandstone, shale, then you get more and more and more and more. And when you get several miles thick of this, the minerals start to complain again. It's like a marriage when it gets in trouble, when the husband's unemployed or something. They say, "You've changed, dear, and I can no longer live with you," and the marriages start to break down. And the first sign of that is when we'll follow what happens to these minerals. Clay minerals are very big. They've got all kinds of different atoms in them. So they're the most interesting when they start to get under pressure. The first thing that happens is absolutely all the water is driven out, and they get really, really flat because of all this pressure. And does anybody know what we call that? When you get a rock a shale that will ring, we say that it's metamorphic. Somebody gave it the name, and what's it called?
Slate.
Slate, yes. So it's used billiard tables, and I guess in Europe they use it for rooftops, slate roofs, but they'd be very heavy. The next step is when the pressure increases even more. You add even more. At the very top, you're adding more and more sandstone, and you're getting more pressure on top there. That's when the magic starts to happen. You actually get new minerals growing out of this slate, which was shale. So something as dull and black as that can actually change into this, just by the atoms rearranging themselves. Again, it's because of all this downward pressure. It likes to form flat minerals like mica. You see a lot of mica minerals being created out of this slate. And this is, anybody know? You probably don't know the name of this one. Schist. And this is called the Manhattan schist, actually, and that's where I found it. My son has a job down there. I got this out of the banks of the East River. So we got up to the point of a schist that new minerals are starting to be created, and they're all nice and flat because the pressure is still very, very directed, very up and down pressure on these minerals. So we add another mile of sandstone and limestone and shale on top. The pressure and the temperature get even higher. Even the schist says, "Oh, I can't live under these conditions." The atoms rearrange themselves again, and you change from something like this to something like this. And then this is the most common rock you see up in the Canadian Shield. That's just about the highest level of metamorphism that you're going to get. And anybody know the name of that? Gneiss. So anytime you look at that, you can say, "Oh, that's nice." Now, because it's a German word, it's spelled a little different, Gneiss, but you just pronounce it nice. So what's happened is these minerals were under so much heat and pressure that they broke down. The marriages of these various atoms just broke down, and they found new partners. And they're not so much concerned with being flat anymore. I believe it's because the pressure is not so much just down. Pressure is more even. The rocks are so deep now that they begin to flow in almost a plastic. Not really liquid, but sort of plastic. So the pressure is more equal around it. So you don't see as many of the flat minerals, but what you do see is the minerals form into bands. Here you can see a very thick band of probably magnetite at the top there. This mineral magnetite, which started out here, and that's the first mineral you see that broke down and formed that rust stain. Well, it's gone all the way through and it's formed itself again. It's happy again under extreme heat and pressure, way miles down below the earth. So, yeah, that's what's typical of a gneiss. The minerals are no longer so much flat, but they form into these layers. So if you're a chef, you can think of it as a schist is like puff pastry, all these layers, and a gneiss is more like lasagna with the noodles or with the layers of noodles and then the cottage cheese and the hamburger. Now this is what happens when we follow the clay through the metamorphic series. So what happens if we followed the sandstone? When we heat that and press it to the same level that, let's jump all the way up to the gneiss level, one of the highest levels of heat and pressure. Does anybody know what sandstone turns into? Anybody know what minerals, what atoms are in sand? Anybody know what sandstone is made of? Silicon and oxygen. It's a very simple formula, and the two of those are like Paul Newman and Joanne Woodward. They get married and they just stay married. The heat and pressure doesn't break them down. What happens is the individual grains of sand will just get welded together into the most perfect rock, quartzite. So if you want a countertop that's never going to go like that, even if you left it outside, you would have a countertop out of quartzite, and that will last 1 billion years. And if we followed limestone, again, let's jump all the way through these stages right up to the gneissic level of heat and pressure. Does anybody know what, this is what it looks like, what limestone changes into? Marble. Again, calcium, carbon, and oxygen. Calcium carbonate. Those minerals are very happy together. You can heat them and squeeze them, and they still stay together. They just sort of merge together into the crystals get bigger, and you get this beautiful, usually white, but you can get colors with impurities. Well, all this is going on. Things are living and dying and getting caught up in these sediments. And what do you call that? Evidence of a past life that we find in, yes, fossil. Right. When you get past the slate level of heat and pressure, you're not going to find any more fossils. They get destroyed. So, and you're not going to find any fossils in igneous rock, because once the rock melts, your fossils are going to be destroyed. So the sedimentary rocks is where we're going to find evidence of past life. These are all coral, and these are about 300 to 450 million years old. And this one I found on the beach. So you see, coral hasn't changed a lot in the last several hundred million years. This is called a brain coral for obvious reasons. And this is
petrified wood.
Very good, yes. Petrified wood. And if you look at this closely, you can see every cell of wood. But in fact, there's not a bit of wood left in this. In fact, most of these fossils are not the original material that animal had as a shell. It's just that when it gets buried gently in the sediment, the groundwater sneaks in and replaces cell by cell the original animal or the original plant. And so you can look at the original structure.